Hello guys, welcome to Backbencher Studies channel. In the last video, we discussed how we can plot the root locus, that is the locus of roots, how the roots vary as the system parameter gain k varies. So we saw so many rules based on two conditions of characteristic equation. They are Evans conditions. So we saw seven or eight rules. So we will be solving in this session. We will be solving an example for plotting the root locus. So let us start our session. So we have a open loop transfer function over here. So we need to sketch the root locus of this corresponding open loop transfer function over here. So coming to step one, we should find out the number of branches of the root locus. So remember the step one states that the number of branches for the root locus is equal to number of poles. So if we see this open loop transfer function, we have zero zeros for this open loop transfer function. We have no zeros for this open loop transfer function, and we have three poles for this transfer function, that is s equal to 0, s equal to -5, and s equal to -10. So this is how we have we have three poles for our open loop transfer function, then we have three branches for this open loop transfer function. And moving on to rule number two, that is the number of branches going to infinite. So the number of branches going to infinite would be n minus p, where sorry p minus z, where p is number of poles and z is number of zeros. So we have three poles and no zeros, so 3 minus 0 gives us 3. So all the three branches of this root locus are going to infinite. So from rule 1 and rule 2, we can say that the root locus will have three branches, and all the three branches going to going to infinite or moving towards the infinite. So moving on to rule 3 or step 3, we need to find out on real axis. That is, if we say that this is the s-plane, then we can say the horizontal axis, that is the real axis, which we can say, and this vertical axis is the imaginary axis. So real part of s is plotted on this horizontal axis. So this is real axis. So on the real axis, which part is lying on the root locus, that we need to find out. That will be given by rule 3. So it states that to the left, so a point on the root locus, a point on the real axis lies on the root locus if the number of poles or zeros, the sum of number of poles or zeros to the right of it must be an odd number. So if we consider any point over here, like this is not breakaway points, consider any random point. For this point to be laid on the root locus, we need to find out the total number of poles and zeros to the right of it. So to the right of it, we have only one pole. So we have one means it is an odd number. So this point lies on the root locus. So we can say that this any point from this region to this region lies on the root locus. But if we take any point here, then we have two poles to the right of this point, so that becoming an even number. So this point or this region on the real axis does not lie on the root locus. However, if we take a point beside this pole, then we have three poles to the right of it, that making that an even odd number. And this portion of real axis, this entire portion up to infinite, will be on real axis on root locus. So based on that, we can identify this green region as the region on the root locus. This orange region is the region which is not present on the root locus, and this green region, this entire green region up to infinite is also present on the root locus. So moving on to rule number 4, we used up to now we used three rules, and moving on to rule number 4, we need to find out the angle of asymptotes. So we saw that in rule number 2, our root locus branches are going to infinite. So what are asymptotes? We already know that the asymptotes are the tangents at infinite for any curve. So we need to find out what are the angles made by these tangents. So for that, we use this formula, which is 2q plus 1 by 180 into p minus z. That means p is the number of poles and z is number of zeros. We have z is equal to 0 and we have 3 poles, so p equal to 3. If we substitute 3 over here, and if we substitute q equal to 1, q equal to 0, in this we have 160 degrees, and if we substitute q equal to 1 over here, that will be 3 into 180 by 3, giving us 180 degrees. And if we substitute q equal to 2, then we have 5 into 180 by 3, that will be giving us 300 degrees. So if we plot these lines, so we have one line which is 60 degrees. So remember, the angle should be measured, positive angle should be measured anti-clockwise. So we have a 60-degree line over here, which is the asymptote, one of the asymptote, and we have another line which is of 300 degrees, and we have another line which gives us 180 degrees. So these three are the asymptotes. So moving on to step number 5, we have centroid of these asymptotes. So all of these asymptotes meet at a single point on real axis. That point we need to find out. So the centroid of this real axis is given by rule 5, which is sum of real parts of poles minus sum of real parts of zeros. So what poles we have is, if we see that we have poles 0 and -5 and -10, all our poles are real. And if we substitute that in this formula over here, then what we are getting is 0, 0 is a pole, and -5 is a pole, and -10 is a pole. So we have the sum of real part of poles minus 0, the sum of real, no, as we have no zeros, we can substitute 0 over here, divided by p minus z. P is 3 and z is 0. So if we kind of do that, then we have our centroid, which is at -5. So if we plot according to this, so this is the plot we have done based on our angle of asymptotes. So these three lines are the asymptotes are meeting on the real line, which is -5. We identified this point. So moving on to next question. So is there any break-even point we need to find out? So based on that, if we find out the characteristic equation, that is 1 plus gs into hs. So if we gs into hs, the open loop transfer function, if we substitute that, and if we find out the characteristic equation, we have s cube plus 15s square plus 50s plus k. So if we write it in k, we have this equation over here, minus s cube minus 15s square minus 50s. So for to finding out the breakaway point, what we need to do is the differentiation of k with respect to s. So if we kind of differentiate this k with respect to s, what we have is minus 3s square minus 30s minus 50. That is what we have. So if we kind of solve that, and we have obtained two roots for this equation, which is dk by ds. So that is minus 2.113 and minus 7.88. So this 7.88 does not actually lie between, because if we see, so minus 2.1 is lying between 0 and minus 5. So we can say all the points are lying on the root locus. So we can take minus 2.1 as a break even point. But minus 7, if we take, that is not, that is in the region which is not on the root locus. So we cannot take minus 7 point something over here. So we already found out the break even point. And if we see that, so the asymptotes are going in such a way that the curve should intersect the imaginary axis. So if we take any curve whose asymptotes are like that, in such a way that it is making 60 degrees with the real axis, the positive real axis, then we can say for sure that it should touch the imaginary axis as well. So for touching the imaginary axis, we need to find out the auxiliary polynomial. If we have a pole or root on the imaginary axis, what is that means is the system is marginally stable. That is, the entire row of this Routh Hurwitz table or Routh array should be zero. So based on that condition, we find out the Routh array for this characteristic equation which is over here. So if we find the Routh array, for that we have s cube, s square, and s power 0. If we kind of substitute that alternatively, then we have this Routh array. And if we do some calculations, so 15 into 50, that will give us 750, minus k into 1, that will give us k by 15, and we have nothing over here, so we have 0 over here. And if we kind of do this multiplication, what we have is k. So in order to intersect this root locus with the imaginary axis, what we need is the auxiliary polynomial. So for that, we need to make an entire row of the Routh-Hurwitz array should be 0. So to make this 0, we have k equal to 750. This k is termed as the marginally stable value of k, for which the system will be marginally stable. So if we take so km is 750. From equating this to 0, we got that. If we find out the auxiliary polynomial, we have 15 into s square plus k into s power 0. So that if we substitute k equal to 750 over here, we have the auxiliary polynomial. And if we kind of solve the auxiliary polynomial, but which is 15s square plus 750 equal to 0, if we solve that, we have s equal to plus or minus j root 50 over here. So these are the 2 points where the root locus intersects with the imaginary axis. So this is how we can find out the root locus cross section with imaginary axis. So we have all of our points, so we can plot the root locus as follows. So the root locus branch is starting from the pole at k equal to 0, and it is kind of moving in this direction because there is a breakaway point at 2.13113 over here. And it is and this branch which is moving, which started at a pole at minus 5, is moving towards the break even point. And these branches are moving in such a way that these asymptotes are making 60 degrees and 300 degrees angle respectively, and intersecting the imaginary axis at j 7.707 and minus j 7.07. And this branch which is starting at this pole at k equal to 0 is moving to infinity at an asymptotic angle of 180 degrees. So this is how it is going. So this is how we can plot a root locus for a given system based on the rules we discussed. That's it for today, guys. If you learned something new in this in this video, please give it a like and please do share and subscribe to our channel.